Welcome to the keynote sections of Reliability-Driven AIOps for Cloud Resilience. My name is Tao Xie. I'm the program co-chair of ICSI 2021. Let me briefly introduce Professor Michael Rui. Professor Michael Rui is a professor at the Department of Computer Science and Engineering at the Chinese University of Hong Kong. Professor Rui has worked on many different areas besides software engineering, including, of course, software engineering, especially software reliability engineering, cloud computing, distributed computing, machine learning, etc. Very long list of different areas focused on by Michael's group. Michael is a IEEE fellow, AAAS fellow, and ACM fellow. He has received many awards. Due to the time limit, I'm not going to list them. Without further ado, let me give the stage to Professor Michael Rui. Michael, please.
Thank you, Tao. Good morning, good afternoon, good evening, wherever you are. So I'm Michael Liu from the Chinese University of Hong Kong. And this PowerPoint file, the picture right there is showing our campus, which is a nice campus occupying the whole mountain in the front and also in the back. So you're welcome to visit Hong Kong, and I'll be happy to host you. The talk I'm giving today is Reliability-Driven AIOps for Cloud Resilience. Modern software systems provide convenient services to our daily lives. In particular, many such software systems are hosted in a cloud to provide their services. Cloud adoption by industry is constantly rising, and cloud revenue continues to enjoy an impressive growth. As predicted in this forecast table, it will reach $354 billion by the year of 2022. The most important infrastructure of cloud computing is the data centers around the world. Data centers are huge hardware and software systems with high-speed interconnection networks. The tremendous complexity of data center operations brings major reliability challenges to cloud computing. Any cloud outages or breakdown will impose huge negative impacts to cloud computing providers. According to Lloyd's report, a major failure that brings cloud outages for 3 to 6 days could result in a total loss of 19 billion revenue, and most of which will not be covered by insurance. So to this end, cloud resilience is very crucial. State-of-the-art cloud reliability is motivated by service level agreement with 5 to 6 nines of availability requirement and demands high degree of automation. Unfortunately, cloud failures often occur to major cloud operators. Cloud reliability issues are mainly due to the fact that tough cloud failures take a long time to mitigate manually. They impose losses and harm customer trust and company reputation, including both cloud providers and the service providers. Worst of all, in a society highly dependent on IT infrastructure, cloud outages can affect everybody's life, just like power outages. Cloud failures are often software-induced or software-related. Traditionally, software reliability engineering, or SRE, aims to solve software reliability challenges by providing reliability models to track software failures. The track failure rates enable engineers to predict software reliability with analytical models, often using just 2 or 3 parameters. My Handbook of Software Reliability Engineering, published 26 years ago, examined this process and introduced the techniques to improve software reliability, including fault avoidance, fault removal, fault tolerance, and fault prediction. This traditional analytical approach is not enough for today's complicated cloud software anymore. We need new term called site reliability engineering, also abbreviated as SRE, interesting enough, to tackle new reliability issues of cloud software and systems. The question is, how do we perform this new SRE properly? Today, data-driven AI techniques with machine learning models have been applied in many domains. There are three major dimensions: data, models/paradigms, and tasks. In computer vision domain, data includes examples like ImageNet and CNN and GNN are popular models, and they enable a number of tasks. In the natural language processing domain, there are various data sources, and RNN, LSTM, and other machine learning models or deep learning models are also available, and they enable quite a few different NLP tasks. In our familiar code-based analytics domain, the data may include GitHub, Stack Overflow. Oh, by the way, I should also mention IBM CodeNet, which was addressed in yesterday's keynote talk. And they will enable a number of tasks interesting to the software engineering community. Other than these models, there are also other learning paradigms, including transfer learning, reinforcement learning can come into play. So in this new domain called data-driven AI operations for cloud, we should also ask the same research question in these three dimensions. In the data dimension, we ask the question, what data to collect in the cloud? In the tasks dimension, we ask the question, what tasks should be pursued for cloud resilience? And finally, we ask, what models and how? To serve various users, cloud computing provides flexible infrastructure containing three major layers, including application layer, platform layer, and infrastructure layer. Besides cloud incidents, customer services can be used to collect most incidents, outages, or dissatisfaction reports from the users. They transfer feedback to on-call engineers, and on-call engineers inspect the status of cloud and discuss the problems and the solutions. This process will generate incident tickets. To get more insights, on-call engineers need more cloud status data from other sources, which include logs, metadata, topology, and alert. These data can be collected in various cloud layers as being shown in this diagram. So many cloud data are actually available. Currently, on-call engineers have different responsibilities, and the cloud incidences are solved separately. This process is being slow and very, very inefficient. The reasons include frequent updated components brought by the popular DevOps paradigm, the complex service dependencies, load balancers, and recovery procedures such as backup and restore. The resulting incidents are often at multiple locations, from multiple resources, and in multiple layers. Humans are not good at solving this large-scale complex problem, but AI is. So this leads to our discussion of AIOps for cloud resilience, which is a data-driven AI approach. We examine the following data sources. Log data contain application logs, system logs, microservice traces. Metadata include utilization of CPU memory disk network utilization and application KPIs. Topology refers to cloud architecture of application layer, service layer, and infrastructure layer. Alerts are data generated by rules. Finally, incident tickets include reports, war room discussions, and chat messages. As we mentioned, traditional software reliability engineering employs 4 tasks: fault avoidance, fault tolerance, fault removal, and fault prediction. For cloud resilience, these 4 tasks can be roughly changed to anomaly detection, failure diagnosis, root cause analysis, and failure prediction. So in a nutshell, AIOps for cloud resilience can employ 5 kinds of data to solve 4 new SRE tasks automatically. Therefore, I organized the technical contents of this talk to include log analysis works, KPI analysis tasks, service dependency jobs, incident management efforts, and finally, the outage prediction. So this work stack includes the techniques utilizing data and resources from the low level to the high level, and the associated task is from easy to hard. Usually we build up from the bottom to the top. So we begin with log analysis, which enables anomaly detection and failure diagnosis. The first step to conduct log analysis is the log parsing. The objective of log parsing is to transform raw log data to structural data, which is convenient for intelligent algorithms to handle. The key problem to solve is to extract event types and the variables in the log messages. This diagram shows how raw log data can be parsed to log events and variables, and there are papers associated with that. So I will skip the details. The log anomaly detection starts with feature engineering to extract the proper system features. After parsing, log volume of log sequences will be partitioned into multiple slices. There are 3 types of methods to obtain these slices: fixed windows, sliding windows, or partitioning by specific identifiers. Then some features like the counting or variable values are extracted from these slides. And next, we feed these features to train an advanced machine learning model, which will capture the intrinsic characters of the log data. Finally, a straightforward anomaly detection algorithm can depict some anomalous data from the output of the models. There are many log anomaly detection methods following this same framework I just described. Most of these methods belong to traditional machine learning algorithms like clustering support vector machine, classification techniques, and frequent pattern mining algorithms. Besides, some new papers discuss how to utilize deep learning models to conduct anomaly detection from the log sequences. This is an overview classification and comparison of these methods from a survey paper recently published. Failure diagnosis tasks aim to find more insights about anomaly and failure because log is the major source for engineers to diagnose large-scale cloud software. Therefore, log-based diagnosis follows a similar procedure in anomaly detection, and let me describe the steps, which include the data collection, pre-processing, feature extraction, and machine learning model application in order to extract the possible issues relating to the cloud failures. So in this work, represented by the bottom paper, SC-Miner is a typical framework to conduct failure diagnosis by reporting buggy functions. The system trace logs contain millions of system calls from the cloud data, which appear to be very difficult to analyze. Nevertheless, these system calls can be filtered and optimized into specific types of system calls associated with the number of the calls. And in machine learning step, therefore, the authors introduce PCA algorithms to find abnormal system call sequences, Consequently, function signatures can be extracted and buggy functions can be identified and ranked. The resulting failure diagnosis have shown to be quite effective. The next task is to use metadata to perform anomaly detection. As an example of metadata, key performance indicator or KPI is one of the most important data in the cloud, which is leveraged to monitor runtime information of a cloud component like network traffic, response delay, or CPU usage. The data can help us to understand health status of the cloud, so we can conduct anomaly detection over KPIs, which may reflect real anomaly within the system. For example, a simple spike in the CPU load and a network inflow may indicate some anomalous cloud status. There are typically univariate KPIs and multivariate KPIs. The anomaly detection approaches on these two kinds of KPIs are quite different. For univariate KPI, each of the KPI is used to monitor specific component, for example, CPU load. But these components are coupled together, which become multivariate KPIs. In most cases, there are fewer anomalies when examining multivariate KPIs, and the parts identified as green are actually normal. Due to the lack of manual labels, unsupervised anomaly detection is required. The intuition of anomaly detection is as follows. Many machine learning-based anomaly detection follow the same framework. It consists of two phases. In the training phase, we use sliding windows to generate data samples. For each sample, we split the KPIs to two parts. The preceding observations in black and the next observation denoted in either blue or red. In the detection phase, we compare the difference between the prediction and the ground truth. If the difference is obvious, then the anomaly is flagged. We found that in many real-world cases, only the rare combination of states in different categories indicates an anomaly. Many experimental investigations are currently being conducted. In the next work, I will examine the logs and KPIs, which can further be correlated to enable failure diagnosis and problem identification. From machine learning viewpoint, anomaly detection and problem identification are equivalent to binary classification versus multi-class classification. So we need to explore the potential solution of problem identification using multi-class classification or clustering methods to group different types of data together. Before exploring KPI data, we can first group log data by exploring cascading clustering algorithms to extract common log sequences. And we found out that after iterative sampling and clustering, most types of log sequences can be categorized into various clusters for further analysis. So we find that the correlation between these two kinds of data and enhance their ability of problem identifications. On the one hand, logs are continuously generated, while on the other hand, KPIs are periodically collected. And KPIs versus logs can therefore be aligned by a fixed time intervals. And we show an overall framework to group logs with KPI changes. After KPI and log alignment, we can attempt to solve the impactful problems, that is, how to identify the reason of the KPI degradation. The target is to identify clusters that are highly correlated with KPI changes. We therefore model the relation between the cluster sizes and KPI values. And we propose a general framework to include log parsing, sequence factorization, cascading clustering, and correlation analysis to find highly correlated KPIs changes a specific pattern of log sequences in order to locate the problems. And we evaluate the method on real Azure data. 3 large-scale data sets were investigated. Our method, called Log3C, performed the problem identification task with high precision and recall, comparing with state-of-the-art approaches. So with the metadata and topology information, we can further investigate service dependency in cloud, which allows failure diagnosis and root cause analysis. This work, represented by the paper on the bottom, investigates correlation to root cause of the microservice platforms in cloud systems, where metadata belong to different services. The connection between services can facilitate the investigation of root cause when anomalies. Combined with metadata and topology, causal analysis method is used to link the correlated services with the observed metadata. Therefore, when an anomaly is detected, the root cause investigation procedure will return top correlated services, which may contain anomalous status. Another related work for the root cause analysis is based on a service call graph. It includes 3 kinds of anomalous metric data: response time, error counts, and queries per second. A service call graph of the target microservice system is first dynamically constructed, which reflects the service dependencies. Based on the graph, possible anomaly propagation chains from the initial anomalous service are analyzed by traversing the graph along anomalous service calls. Finally, from multiple anomaly propagation chains, several root cause services can be reported. Alert aggregation, on the other hand, in AIOps, can also enable failure diagnosis and root cause analysis. To assist engineers in failure diagnosis, 2 tasks can be performed, which are alert aggregation and root cause recommendation. Alert aggregation is to group incidents caused by the same failures. Engineers can remain focused on a small set of incidents to understand the nature of the failure. Root cause recommendation, on the other hand, is to find the subset of the aggregated incidents that are likely to be the culprits of the failure. This figure here shows that when service A encounters a failure, the failure may propagate to its neighboring services. Incident aggregation can separate these incidents from other irrelevant ones, such as the blue incidents. So engineers only need to be focused on the red incidents. To address these challenges, we propose an incident management framework based on graph representation learning. As shown in this figure, our framework consists of 4 steps, which are cloud failure detection, KPI-based community detection, graph representation learning for incidents, and online incident aggregation and root cause recommendation. In the first step, we first detect incident burst, which often indicates the occurrence of cloud failures. In the second step, we use more fine-grained cloud monitoring data, such as KPIs, to auto-complete the graphs, which recovers the big picture of the failure. Next, we leverage graph representation learning to learn vector from each of the incident, which encodes its interactions with other incidents in temporal as well as topological dimensions. Finally, with the representation vector of each incident, the task of incident aggregation and root cause recommendation can be naturally performed. The evaluation on real data sets generated by a top public cloud shows that our approach achieves obvious improvement compared with the other state-of-the-art methods. One important AIOps function is incident management, where incident tickets can facilitate failure diagnosis and root cause analysis. Although modern incident management systems have become highly automated, we still observe significant delays in different incident management phases, such as critical incident detection, impact scope identification, and root cause analysis. We are therefore motivated to have a clear understanding about this phenomenon as well as the underlying reasons, because this can provide us with an important guide to build more reliable cloud systems. Incident management procedure includes 3 major steps: detection, engagement, and mitigation. The key indicators to evaluate the whole procedure of incident management includes incident reporting by time to detect, incident triage by time to engage, and incident mitigation by time to mitigate. When a failure is detected, service providers should quickly mitigate the problem, which, however, is challenging. These challenges include large volume of current incidents, failures being cross-regional, and intrinsic complexity of the cloud systems. We have conducted an empirical study on incidents management. Our analysis on incident severity found that low and medium incidents together take up more than 90% of the total. The number of high incidents drops significantly, ranging from 1.2% in network service to 5.4% in data center management. Critical incidents account for less than 0.5%. However, such incidents are great threats to cloud reliability and should be addressed carefully. We also calculate incident fixing time. And counter-interactive finding is that compared to high incidents, low and medium incidents require more time for mitigation. It may be due to the fact that they were low priority issues. Engineers will not address them immediately. However, regarding critical incidents, more often than not, they are most time-consuming because most of them only happen once. Engineers will need a long time for such brand new failures to be handled properly. We categorize the incidents root cause into 6 classes, for example, network issue, human error, so on and so forth. From this table, we can see human error and network issue are 2 dominant root causes, accounting for more than 37% and more than 30% respectively. Each of them has its own subcategories. The last AIOps application is outage prediction, where alert data can be employed for failure diagnosis and failure prediction. Cloud components usually trigger some alerts indicating anomaly behavior or failures. But due to fault-tolerant architecture, users are often not aware of such alerts. So users may be happy when some instance of failure occur in the cloud system because they are being tolerated. However, when the situation becomes worse, some severe fault happens and the cloud could become unavailable, causing cloud outages. To prevent such cloud outage, the paper shown in the bottom proposes to first detect some alerts and make prediction on the possible outage. It utilized Bayesian network to construct dependency among alert signals and conduct failure diagnosis from historical failure data. For example, a website application outage, when detected, is highly related to time shifting, storage testing, and website servicing. And after data analysis and augmentation from this Bayesian network, a classification model can be trained to link the observed alerts to the cloud outage. The authors of the paper evaluate this method called AIR Alert on Microsoft Azure dataset. Compared to other traditional methods, AIR Alert achieves impressive results on outage prediction tasks with high precision and high recall. This is achieved for both component level outage prediction as well as service level outage prediction. Okay, so here comes my conclusion on this talk. So we asked the question, why cloud resilience is needed in a cloud for the AIOps operation. And this is essentially because of the pursuit of reliability is high. And we need to go from automatic to intelligent operation, from the reactive commands to the proactive commands in order to handle the cloud failure proactively. And we examine 5 important data sources: log, meter data, topology, alert, and incident tickets. We also ask a question, how AIOps achieve reliability goals. And this is because that there's a large number of machine learning algorithms that we can apply. And as a result, we examine 4 various tasks in AIOps, including anomaly detection, failure diagnosis, root cause analysis, and failure prediction. And the key is intelligent algorithms need to be designed with human experts' experiences. So to probe further, what comes next is the question, how can we integrate human knowledge with algorithms automatically and comprehensively? And that means that the further investigation on AI and software engineering will be needed. To further dig into AIOps research, therefore, we establish an automated, reliable, intelligent software engineering lab, or a RISE lab, aiming to bridge artificial intelligence and software engineering. You are welcome to scan the QR code over here and take a look at the RISE lab website that we just constructed. Such efforts are also common interest to many researchers in ICSI, whom you can meet at the workshop on cloud intelligence on May 29th, just 3 days from now. Thank you for listening to this talk.
Great. Thank you, Michael, for a wonderful talk. Next, we are in the Q&A section. For our audience, please type your questions in the chat for this section. And then I will speak up your question to Michael so that Michael could respond. We have a couple of questions from Srida already. The first one is really simple. It's a more clarification question. Does AIOps mean AI applied to DevOps or cloud or both?
So my understanding is that AIOps is a general framework, so it can include both. AIOps idea is apply machine learning technique for the IT operation. Right? And IT operation can include the cloud or can include infrastructure, which includes the hardware, software, where they are interconnected together. And the key thing is that there's a lot of data, and as a result, AIOps is related to the operation, how this data can be properly analyzed. And of course, it's due to the DevOps kind of paradigm, okay? But it's more focused on the operation side. Of course, the operation side can be examined properly in order to sort of feedback to the development side in order to make a better, reliable development of the systems. So I would say that AIOps actually can be applied to both, even though it's more focused on the operation side. And it was due to the DevOps kind of paradigm, which is permeates now in the IT development.
Great, thank you. The second question from Srida is below. It's often the case that cloud services start causing issues after they are deployed because the developers may not be aware of the required scale. Is there any way to simulate the cloud usage scenario, like the large-scale usage, without violating privacy of the data and services?
There's already some effort in order to simulate the cloud, and as a result, some data can be generated. The advantage of that, of course, is that you can do experiments on the experimental cloud without affecting the real cloud. But the disadvantage is also obvious. That is, a lot of complicated scenario may not be available when you do the simulation kind of approaches. Okay. And usually on the software level, the dependency of the service is relatively easier to handle because you can do simulation on the software side. The difficult part is that the underlying infrastructure of the cloud may have the failures coming from the hardware, from the networking, and from many other kind of devices, which may be hard to simulate without using the real devices. And that actually make it a bit more difficult. So usually my understanding is that major company will have their experimental cloud with the real devices, but those cloud is experimental, so they can conduct real experiments on those cloud without affecting the real operation. Okay. And those experimental cloud represent a more realistic environment which can be experimented on. Nevertheless, I think the private, like a university, we are poor guys, right? So we can only buy a few big machines and then do some kind of simulation. And normally we try to do that in a higher level to understand different kind of impact. But eventually, if we want to do a full scope of the cloud simulation, that is relatively more difficult. So we need to call for more data that can be shared among different parties, including the academia, and more importantly, is from industry.
Great, thank you. Next question is from Lutz. Can or will those techniques that you described be packaged as easy-to-use libraries so that a cloud operator can hopefully use them basically in a more like a quick and easy way of adoption of these wonderful techniques? Or like maybe they are too specific, case by case, you had to customize and deploy with much effort.
Yeah, Tao, you also know this how software works. That's why you already addressed part of the answer. And the answer is what Tao just mentioned. Usually the problem is being solved in an isolated domain, such that the solution might be very related to a particular application in the cloud. However, this kind of package can be put together. So usually researcher, when come up with a research results, it has to be general enough in order to be able to publish in ICSI, right? So it is not just engineering effort, it is also researcher need to expand it to something that can be generalized. And I believe that's really possible because a more general problem can be solved in such a way that those problem solutions can be packaged together. So example is like there are certain anomalous patterns. We can try to sort of describe the anomaly patterns, say in the KPI kind of data, and try to produce certain kind of KPI anomaly detection packages. Something very similar to the word embedding or graph embedding. Why can't we have some kind of the KPI embedding which relate to the anomalous kind of situation? Okay. And indeed, this kind of effort to come up with a general package, which can be utilized not only by researchers, but also by the practitioners, is one of the research directions we are aiming at. And remember, these are all data-driven approaches, but the nature of those failures come from the operation of the cloud, and a lot of symptoms are related to how software handle those situations. So their behavior are really software-intensive or software-induced. And as a result, this pattern, when apply machine learning to those patterns and try to analyze and come up with some knowledge about that, it is really an excellent example to interact with AI as well as software engineering. And the answer to the question is yes, I believe it's possible in order to sort of publish a library of certain kind of anomaly detection algorithm related to the cloud operation so that it can be publicly available for general usage.
Great, thank you. Next question from Long. Like you mentioned, like some techniques on detecting failures and then developer will fix the faults related to the failures. Do you think AIOps also consider the work about verifying or validating the updated fix, right? It's more like fix validation, such as conducting fault injection or chaos engineering on the fix?
Yes, this is certainly a step further. That is, you want to automatically remove the bug, not just fix your failure, but also try to improve it so that the software or the system can be more robust and more resilient. And currently, the major problem with this is that there's not enough data. Normally, whenever there's a problem occur, there's a ticket to be filled, and there's a description of that. When the problem is being fixed, usually it takes days or even weeks later, particular major problems. And the solution report is being filed usually in the natural language kind of format. And it's not inside the system, but instead it's some kind of in the documentation. So often when the solution is found, it cannot be automatically retrieved. In other words, it's unstructured data. And it will, however, be possible to analyze those documents in order to come up with a more general solution so that similar problem occur later on can be sort of solved using the previous knowledge. I would just say that currently, because of the lack of data, and this kind of work is still being continuous. But I think that's the direction to go for the next step, which I haven't covered, but that would be important next step to go. In other words, we have this idea called self-driving car, and we could also have the idea of self-driving clouds in such a way that it can fix itself. And that certainly is the ultimate goal for the AIOps operation in the cloud computing environment.
Great, thank you. And like your research on this direction, at least much of it has been conducted in collaboration with industry, right? So
yes.
One question from Yun is like, are there any popular open source deployed subject cloud system for experiments on those research work without collaborating or being kind of like relying on industry partners?
Yeah, that's a good question. And the answer is yes and no, because yes means that actually there's some data. We also use public domain data in order to perform the experiments. Some of the data that I published or presenting in my talk was openly available. Refer to the paper and you can find them. Unfortunately, the real data or large-scale data, indeed, you need to work with the industry partner in order to get the information. And you can maybe get with them by sort of close collaboration with them. But I think there are more and more effort where industry is willing to open their data, at least partially, so that the data, once collected, can be used to facilitate different kind of research. I think this is like 20, 30 years ago that the people are not willing to sort of open their code, right? And quick enough that the GitHub is available and people finding that use the code is really increasing the productivity. I think the cloud provider eventually may realize that if they make the cloud open to the public, doing more research for them actually will help them rather than hurting them. Because the security and privacy is another level that they can handle. But in terms of the software engineering level, try to make the cloud to be more productive, try to make more people developing their application on the cloud is some sort of effort they are willing to see. That's kind of my prediction. So openness of cloud, I think, may become the trend in the next next few years. And as a result, we can expect that there'll be more open data available for the cloud source. And currently, I know that there's effort where the cloud data is being published in order to call for competition for analyzing the cloud data so that it can make better prediction. And this is very much like 15 years ago when there's challenges, Netflix challenges about they publish this movie data, right, about recommendation, and there's a lot of competition about those, and people are highly interested in the recommendation system for the movie and later for many other products. I think this kind of effort of open the data source from the cloud will eventually enable more sort of interest of studying about the data analytics for the cloud environment. So I would hope that the industry are willing to see the benefit and they will be willing to open this kind of data more and more. And to my understanding, the company I work with, they tend to be seeing the same way as well.
Great. We have 18 seconds. I don't think we could fit a question and answer the last one into 10 seconds now. So let us thank you again for a wonderful talk. For remaining questions, we could go to a discussion room. Thank you.
Thank you very much. Thank you.